We're now going to start a new topic in Math 7, which is vector spaces. Vector spaces are supposed to be mathematical objects which generalize the idea of column vectors or row vectors or matrices. So in the following sense, so let's think about what the following things have in common. So here is R to the n, that is the set of all height n column vectors with real number entries. C to the n, that's the same thing only with complex numbers instead of real numbers. M subscript m times n of R, the set of all m by n matrices with real number entries. And of course the same thing with complex number entries. What do these things have in common? Well, one collection of things they have in common is that they come equipped with an addition operation. You can add any two real column vectors of the same height. You can add any two complex column vectors of the same height. You can add any two matrices of the same size. And they come with a scalar multiplication operation. You can multiply an element of r to the n by a real number and get another element of r to the n. And similarly, you can scalar multiply a complex matrix by a complex number. And you can scalar multiply a real matrix by a real number. But what's more than that, those operations of addition and scalar multiplication obey similar rules in every single one of these cases. For example, the statement that if you have a scalar a and you multiply it into x plus y, then the result is the same as a times x plus a times y. Well, that's true whether or not x and y are real column vectors and a is a real number, or x and y are complex column vectors and a is a complex number, or x and y are real matrices of the same size and a is a real number, or x and y are complex matrices and a is any complex number. And there are many other properties to do with addition and scalar multiplication and how those two things interact, which are common to all of the structures we've seen. So when we define vector spaces, those things are defined to be spaces which have their own notion of addition and scalar multiplication by a certain type of scalar, in our case real or complex numbers, and which obey all of the common rules which addition and scalar multiplication have for real column vectors and complex column vectors and real and complex matrices. And we'll see that actually a great variety of structures, not just these column vectors and matrices, obey all those same rules. So let's now be specific about exactly what rules we're talking about here. Those rules are called the vector space axioms, and they're what we use to define a vector space. So we'll start off with the notion of a real vector space. A real vector space is a set V that contains a special element 0 subscript V called the zero vector, and an operation plus called vector addition, which combines two elements of V into another element of V, and a way to multiply elements of V on the left by elements of R, which is called scalar multiplication, such that the following long list of properties holds. For any three things in our vector space, u, v, and w, and for any two real numbers, a and b, all of the following 8 properties have to hold. So the first one says that if you add the zero vector to something on the left, then you get that same something again. 0 plus u is equal to u again. Secondly, remember this must be true for all u, v, and w in v. And what part 2 says is that there must exist another vector x in v such that x plus u is equal to the zero vector. That's called an additive inverse for u. Thirdly, vector addition is associative. U plus, in brackets, v plus w is the same as u plus v, in brackets, plus w. In fact, that simple rule enables you to remove brackets from any addition operation, no matter how many summands it has. So it tells you that any way of bracketing a sum of any length always has the same value. Part 4 says that addition is commutative. It's always the case that u plus v is equal to v plus u. And then the remaining parts are to do with scalar multiplication and its interaction with addition. First, two things which are solely to do with scalar multiplication. If you multiply a vector by 1, if you scalar multiply a vector by 1, you don't change it. 1 times u is always equal to u. The next part says that there is a kind of associativity property for scalar multiplication. If you work out b times u and then multiply that by a, then that's the same as multiplying a by b and then scalar multiplying that into u. So here a and b, I remind you, are any scalars, any elements of the real numbers, and u is any vector, any element of the vector space capital V. So the final two axioms deal with how scalar multiplication and vector addition interact. These are kind of distributivity properties. The first one says that if you do a plus b and then you scalar multiply that into u, that's the same as the vector addition of a times u and b times u. And property 8 says that if you do a scalar multiple a times a vector sum u plus v, that's the same as the vector sum of a times u and a times v. So those are our vector space axioms. Any set with an addition, a multiplication, and a special element 0v obeying those 8 axioms is called a real vector space. We also have a definition of a complex vector space, which is precisely the same definition as before, except replacing the real numbers with the complex numbers. So in a real vector space, you are allowed to scalar multiply by real numbers, and in a complex vector space, instead, you are allowed to scalar multiply by complex numbers. Apart from that, everything is exactly the same. So to summarize, in a vector space, all of the usual rules of matrix addition and scalar multiplication must hold for the scalar multiplication and the addition in that vector space, even though in general the elements of a vector space can be anything at all, not just matrices and vectors. We're about to see some examples of vector spaces, and you will see that the elements of vector spaces may not be vectors or matrices at all. They may be something completely different, as long as they obey these rules. And the other thing you should notice from these rules is that they really are just familiar properties of matrix or vector addition and scalar multiplication. So before I move on and do some examples, let's think about what the role of the real and the complex numbers are in this definition. So in a real vector space, you can scalar multiply by elements of the real numbers. And in a complex vector space, you can scalar multiply by complex numbers. That's the only role that the fields R and C have to play. And now it's possible to use other kinds of numbers for scalar multiplication, and all the vector space theory that we're about to develop still be true. Any example of what's called a field will do. But we're not going to go into this in 0007. In 0007, we only care about vector spaces over the real numbers or over the complex numbers. When we say over the real numbers, I mean a real vector space. And a vector space over the complex numbers means a complex vector space. So one final bit of terminology before I move on. We often want to talk about vector spaces, and we're going to say something that's true about any kind of vector space, a real vector space or a complex vector space. But we want to have a symbol which refers to the numbers we're allowed to scalar multiply by, which in our case might be the real numbers or the complex numbers. So we'll do that by using a symbol F, which might be R or might be C. So when we write F vector space, what that means is, so this means an R vector space. So a real vector space, or C vector space, which refers to a complex vector space. So the F is just a stand-in for either R or C. So the reason we would want to do this is because basically the properties of real vector spaces and the properties of complex vector spaces are precisely the same. So we'll often just want to talk about an F vector space when we're talking about something which is true for any kind of vector space and where we want to specify where the scalars are coming from. So time for some examples. Let's look at some example vector spaces. First of all, the examples we talked about on the title slide. R to the n and C to the n are real and complex vector spaces where the vector addition is just normal vector addition and the scalar multiplication is just normal scalar multiplication, and where the 0 vector is just the normal 0 vector, what you normally think of as the 0 vector. So R to the n is a real vector space, you can multiply by real numbers, and C to the n is a complex vector space because you can scalar multiply by complex numbers. The other example we saw previously was vector spaces of matrices. The set of all m by n matrices with real entries is a real vector space when you give it the ordinary matrix addition and the ordinary matrix scalar multiplication by real numbers, and when the 0 vector is the ordinary 0 matrix, m by n 0 matrix. And similarly for complex matrices, the complex matrices form a complex vector space with the usual 0 matrix and matrix addition and matrix scalar multiplication. So let's look now at some different looking examples. First of all, a slightly trivial looking example, which is just a set containing a thing called 0. So a set with one element only called the 0 vector is a real or a complex vector space when you give it the addition, which is specified just by saying 0 plus 0 is 0, and the scalar multiplication, which says that when you multiply by any scalar, you just get the 0 vector again. So that obeys all of the axioms. This is a vector space called the 0 vector space. Next, let's look at some examples consisting of polynomials. So R square brackets x means the set of all polynomials in a variable x with real number coefficients. So the set of all things of the form a0 plus a1x plus a2x squared up to anx to the n for any n greater than or equal to 0, and any scalars a0, a1 up to an. We can then do addition and scalar multiplication on those things. You know how to add two polynomials and collect the coefficients together. You know how to multiply a polynomial by a real number. And when you do that, you produce something which is a real vector space. The 0 vector is just the 0 polynomial, so the constant polynomial whose value is 0. So just to emphasize, this would contain polynomials of all kinds of different degrees. So the constant polynomial 1 would be in there, and the constant polynomial 0 would be in there, and the polynomial x would be in there, and 1 plus x cubed would be in R of x. All kinds of polynomials are in there, and it forms a real vector space when you give it the usual polynomial addition and scalar multiplication. And of course you could think about complex polynomials as well, and those would be a complex vector space. You can also look at polynomials where you restrict the degree. So R square brackets x less than or equal to k, or as we will sometimes write it instead, you may see those symbols the other way round, R less than or equal to k of x means exactly the same thing. That means all the polynomials of degree at most k in one variable x with real coefficients. So all things of the form a0 plus a1 times x plus a2 times x squared and so on up to ak times x to the k, where x is a variable and indeterminate, and the a0 up to ak are real numbers. And again, this is a real vector space where you give it the normal polynomial addition, normal way to multiply a polynomial by a real number, and the 0 vector is just the constant polynomial with value 0. That is a real vector space. And of course you could replace the real numbers with the complex numbers and get a complex vector space. So that example is important because it's an example of a vector space where the elements of the vector space are not, in the traditional sense, vectors. So they're not column vectors or matrices or anything like this. We'll still call them vectors. We often call the elements of a vector space vectors, but it's important to remember that there is no restriction on what the elements of a vector space look like. As long as there is a 0 vector and an addition and a scalar multiplication which obeys all the vector space axioms, then it is a vector space no matter what the elements look like. Next, wrong tool. Next, let's look at this set here, which is another example of a vector space where the elements are not in the traditional sense vectors. So curly F here is the set of all functions from the real numbers to the real numbers. So a very big set. We can define a addition operation on the set of all functions from R to R by defining f plus g to be the function which sends an input x to the output f of x plus g of x. So that makes f plus g into a new function. That's defining an addition operation on the set of all functions from R to R. We can also define a scalar multiplication on that set. If you've got a function f from R to R and a real number a, you can define a times f to be the function which sends an input x to the output a times f of x. So that defines a scalar multiplication on the set curly f. And there's also a special element of curly f which we write as 0 subscript f, which is just the constant function which is always 0. So 0 subscript f is always 0 no matter what its input is. And if you make those definitions, you've defined a way to multiply such a function by a real scalar. You've defined a way to add two such functions, and you've defined a 0 vector, a 0 function called 0 subscript f. Then these things obey all of the axioms on the previous slide. So that curly f then becomes a real vector space. And of course you could do the same thing with complex functions as well. The set of all functions from the complex numbers to the complex numbers would be a complex vector space when you give it the same definition of scalar multiplication and addition and the 0 vector. So those are some examples to show that a vector space is a very general concept. In fact, we'll see even more general examples than the ones here, and that the elements of a vector space don't necessarily have to be vectors. Okay, that's the end of our first lecture about vector spaces.